The first thing that shocks most people is realizing we're still living inside an ice age. Not a movie-style wasteland of blizzards and glaciers swallowing cities, but a long-term geological phase that has shaped every coastline, every migration, and every creature that ever roamed the northern half of the planet. This phase began roughly 6 million years ago, and even though the ice sheets retreated thousands of years ago, the Earth remains in the interglacial breathing space of a much larger rhythm. It's a rhythm so precise it feels engineered. Every 100,000 years the planet freezes, reshapes itself, then thaws in a cascade of meltwater and chaos. The pattern is ancient and relentless, and understanding it means understanding why entire species rose to dominance, then vanished like they were never here. But before we jump back in, drop a comment letting us know what time you're tuning in and where you're watching from. We love seeing how far our episodes are reaching. And don't forget to hit that subscribe button. It really helps us keep bringing exciting topics here on the Primal Roots channel. The strangest part is that the force behind this cycle doesn't begin on Earth at all. It starts with the geometry of our orbit, the tilt of our axis, and the slow wobble that shifts the seasons over tens of millennia. These motions, subtle and silent, determine how much summer sunlight hits the northern continents. And those continents, more than any other place on Earth, decide whether the planet plunges into deep freeze or remains relatively warm. When northern summers weaken just enough, the previous winter's snow lingers, piles up, compresses into ice, and eventually grows into ice sheets taller than skyscrapers. Their white surfaces bounce sunlight back into space, cooling the atmosphere further and encouraging even more ice to spread. It's a self-reinforcing system, small orbital changes triggering massive planetary consequences. When those ice sheets expand, the world doesn't just cool, it transforms. Oceans shrink as water locks into frozen continents. Sea levels fall by more than 120 meters, exposing land bridges that humans and animals cross without realizing those pathways are temporary. Africa and the Arabian Peninsula connect. Siberia and Alaska become neighbors. Britain becomes an extension of mainland Europe. Regions that today are lush forests turn into windswept plains where cold-adapted mammals thrive. Enormous grasslands stretch across the northern hemisphere, dotted with hardy shrubs, alpine herbs, and the footprints of creatures that defy imagination. Woolly mammoths, giant sloths, armored glyptodonts, and saber-tooth predators that depended on the fragile stability of this icy world. Humans evolved during these cycles, shaped by the cold as much as by their own ingenuity. Early Homo species adapted to changing climates repeatedly, learning to hunt new animals, survive shifting landscapes, and move as the ice advanced or retreated. Neanderthals developed powerful bodies and wide nasal passages suited for frigid, dry air. Denisovans persisted in high-altitude regions long before modern physiology could have handled that environment. And Homo sapiens, emerging from Africa, entered a world where climate wasn't just background. It was a relentless force that created both opportunity and danger. Every expansion of grasslands invited migrations. Every retreat of forests pushed populations into contact or conflict. The Ice Age climate was not static, but pulsed like a heartbeat, each pulse carrying consequences for life everywhere. The deeper scientists probed into ice cores and ocean sediment layers, the more consistent the patterns became. The 100,000-year cycle is dominated by the change in Earth's orbital shape, its eccentricity, driven mainly by gravitational interactions with massive planets like Jupiter and Saturn. When the orbit becomes more elongated, seasonal contrasts increase. Winters grow harsher. Summers weaken just enough that ice stops melting completely. And once a snowpatch survives a single summer, the next winter adds more, then more after that, until the snow becomes a sheet of ice kilometers thick. Alongside eccentricity, smaller but significant cycles, changes in axial tilt and the slow wobble called precession, fine-tune the planet's energy balance. Together, these three cycles act like gears in a cosmic mechanism, gradually shifting Earth from warm periods to frozen ones in predictable intervals. During the coldest phases, the world doesn't just grow quieter, it becomes a battleground for survival. Strong winds blast across exposed plains, picking up dust and dropping it in thick layers that can still be measured today. The Sahara expands, the Amazon shrinks. Rainfall decreases in many regions because colder oceans produce less evaporation. In North America and Northern Europe, ice sheets the size of continents reshuffle rivers, scrape away mountains, and carve enormous basins that will one day become lakes. Even the planet's crust bends downward under the weight of the ice, altering everything from drainage patterns to volcanic activity. Nothing escapes the influence of the frozen giants that dominate the landscape for tens of thousands of years. And yet, life doesn't merely endure, it adapts. The so-called mammoth steppe becomes one of the richest ecosystems Earth has ever seen. Herds of woolly mammoths, steppe bison, wild horses, and reindeer move across endless grasslands. Woolly rhinos use their massive front horns like snowplows, sweeping aside drifts to reach buried vegetation. Giant ground sloths, slow but immensely powerful, dig massive tunnels into hillsides for shelter, leaving behind underground labyrinths large enough for a person to walk through. Glyptodonts, living tanks with armored shells and clubbed tails, graze along riverbeds, unbothered by most predators. And towering above them all, the saber-tooth cats rule the hunt, equipped not with bone-crushing bites, but with precision tools designed to deliver fatal strikes to the softest parts of their prey. Humans played their part in this frozen world as both participants and observers. They followed the migrations of herds, used fire to shape vegetation, carved tools from stone, bone, and ivory, and painted the walls of caves with images of animals they depended on. Their survival strategies were tied to the rhythm of glacial cycles. When grasslands spread, they moved into new territories. When forests returned during warm phases, they adapted again, changing their diets, tools, and social structures. And as climate shifted faster during some transitions, especially the rapid warmings toward the end of the last glacial period, humans found themselves facing cascading ecological changes that challenged even their adaptive abilities. What makes this cycle so fascinating is that it's both fragile and unstoppable. A slight shift in solar energy triggers enormous reactions. Ice sheets grow slowly, taking tens of thousands of years to reach maximum size. But once the orbit shifts again, they can collapse astonishingly fast, dumping trillions of tons of meltwater into the oceans. These melt pulses disrupt ocean circulation and cause climate whiplash across the globe. Forests race across continents, deserts retreat, rain belts move. Species that thrived in the cold disappear as their habitats vanish. Others expand. Humans, now equipped with evolving technologies, take advantage of these transitions and sometimes accelerate the decline of species that once dominated the world. The story of Earth's 100,000-year cycle isn't just the story of ice. It's the story of how cosmic mechanics, climate, biology, and human evolution are tied together. The rise and fall of megafauna, the migrations of ancient populations, and even the origins of agriculture were all shaped by this repeating pulse. Understanding it reveals not just our past, but the foundation of everything living around us today. The world that emerged as the last glacial period reached full strength was unlike anything recognizable today. Immense walls of ice dominated the northern hemisphere, reshaping the atmosphere, redirecting winds, and bending the Earth's crust under their weight. The planet entered a phase where frozen continents governed climate patterns with near-total authority, dictating where life could exist and how ecosystems evolved. The transformation wasn't subtle. It was a planetary overhaul on a scale no modern environment can match. The Laurentide ice sheet in North America spread from the Arctic deep into the territory that is now the northern United States, blanketing the continent beneath layers of ice that could reach 3 kilometers thick. In Europe, the Fennoscandian ice sheet consumed Scandinavia, the British Isles, and large parts of Russia and Germany, grinding down bedrock and leaving behind valleys and basins that still define the landscape. Together, these masses locked away so much water that sea levels fell dramatically. turning shallow seas into plains and exposing land corridors that altered the course of animal migrations and human movement. The coldest interval, known as the last glacial maximum, occurred about 20,000 years ago. Temperature was only a few degrees lower than modern averages, yet those few degrees represented an enormous removal of heat from the entire climate system. Oceans cooled, evaporation weakened, and worldwide humidity plummeted. The atmosphere grew dustier as strong, dry winds eroded unprotected soils and carried sediment across continents. Some regions received so little rainfall that they resembled polar deserts. Others experienced violent storms, triggered by thermal contrasts between ice surfaces and warmer air masses in surrounding latitudes. Vegetation responded in ways that reshaped entire continents. Tropical forests shrank into pocket refuges. Temperate woodlands retreated as grasslands and steppe environments expanded. Much of the northern hemisphere became a mosaic of tundra and cold prairies, filled with hardy grasses, sedges, and low shrubs that tolerated extreme temperature swings and nutrient-poor soils. This ecosystem supported some of the largest herbivore populations Earth has ever seen, turning the mammoth steppe into an engine of productivity during a time most imagine as barren and inhospitable. These environments were home to a caste of species that pushed biological adaptation to its limits. Woolly mammoths roamed in vast herds, equipped with two-layered fur coats, fatty insulation, and blood chemistry uniquely suited for freezing temperatures. Their compressed, high-domed skulls contained extensive sinus systems that warmed cold air before it entered their lungs. Nearby, woolly rhinoceroses plowed through deep snow with their massive anterior horns, uncovering buried vegetation. These rhinos, larger than any living species, carried dense fur and thick skin, capable of enduring prolonged exposure to temperatures far below freezing. The American continents hosted their own giants. Ground sloths, relatives of the small, tree-dwelling species alive today, grew to the size of elephants. Their powerful limbs and shovel-like claws allowed them to dig immense burrows into hillsides, creating underground chambers that offered thermal stability during harsh seasons. These burrows, discovered in South America, reach dozens of meters in length and display claw marks that perfectly match the anatomy of extinct sloth species. Glyptodonts, armored mammals resembling oversized armadillos, wandered grasslands with shells as hard as stone and tails tipped with heavy spiked clubs capable of breaking bones with a single strike. Predators, shaped by the demands of hunting massive prey, displayed adaptations equally remarkable. Saber-tooth cats relied on precision rather than crushing force, using muscular forelimbs to pin large herbivores before delivering lethal bites to vulnerable areas. Their elongated canines, fragile compared to modern big cats' teeth, were designed for targeted strikes that caused catastrophic blood loss. In the Americas, dire wolves hunted in cooperative groups, their powerful jaws suited for cracking heavy bones in pursuit of high-calorie nutrition. Europe and Asia were home to cave lions larger than any lion alive today, occupying territories of immense size and competing with humans for the same prey. Human and hominin populations experienced the effects of glacial expansion in direct and sometimes brutal ways. Neanderthals had already survived multiple cycles of advancing and retreating ice. Their compact bodies reduced surface area heat loss, and their broad noses warmed and humidified frigid air. They constructed shelters, used fire extensively, and manufactured complex stone tools with planning and precision. Their survival strategies reflected deep familiarity with cold environments. Archaeological evidence shows that they hunted large herbivores, processed carcasses with efficiency, and likely stored food in frozen ground when temperatures were low enough to preserve meat naturally. Modern humans entering Eurasia encountered not only a challenging climate, but also established hominin populations and ecosystems dominated by megafauna. Their success relied on flexible technology, stone blades designed for high efficiency, composite tools, expanded networks for exchanging resources, and clothing crafted from hides tailored with bone needles. These innovations allowed humans to push into regions previously unreachable. As they spread across Europe and Asia, they encountered rapidly shifting landscapes driven by glacial dynamics. Vegetation belts moved, rivers rerouted, and coastlines receded far from present-day positions. In many regions, humans followed migrating herds, navigating open grasslands that stretched for hundreds of kilometers. Fire became a tool not just for warmth, but for landscape management. By burning vegetation deliberately, humans maintained open habitats that attracted herbivores and prevented forests from taking over productive hunting grounds. This practice created a feedback loop in which ecological engineering supported stable populations of megafauna, at least until warming trends disrupted the balance. When temperatures fluctuated rapidly, ecosystems responded with surprising speed. Even during the glacial maximum, climate was not constant. Short-term oscillations caused abrupt warming and cooling events. Some lasted centuries, others only decades. These pulses shaped plant distribution, altered migration patterns, and forced both animals and humans to adapt quickly or relocate. DNA from sediments in permafrost has revealed that species ranges shifted dramatically in response to these climatic swings, leaving behind a patchwork record of survival and local extinction that depended on microhabitats and timing. Ice sheets themselves acted as engines of change. Massive glaciers carved valleys, scraped away soil, and redistributed sediments across wide areas. When they advanced, they crushed forests and redirected entire river systems. When they retreated, they left behind landscapes of moraines, meltwater channels, and vast proglacial lakes. These lakes sometimes grew unstable as ice dams weakened. Their sudden drainage events released torrents of water capable of reshaping continents, scouring plains, and injecting freshwater pulses into oceans. The atmosphere was equally dynamic. Cold, dense air spilling off the ice sheets generated strong katabatic winds that intensified dust production. Layers of loess, fine, wind-blown sediment, accumulated across large regions of China, Europe, and the Americas. These deposits provide a detailed climate archive, recording shifts in wind strength, temperature, and moisture across tens of thousands of years. They reveal a world perpetually adjusting to the balance between ice and sunlight. Despite the harshness of the landscape, the last glacial maximum was not an age of ecological collapse. It was a period of extraordinary biological richness, built on the stability of cold-adapted ecosystems. The mammals that thrived during this time were specialists with long evolutionary histories, tied to open grasslands and cooler climates. Their existence depended on the persistence of these vast steppe environments. As long as cold temperatures kept forests at bay and maintained high nutrient cycling in the soil, the mammoth steppe remained one of the most productive ecosystems on Earth. But the seeds of transformation were already present in the shifting orbital mechanics of the planet. As northern summers gradually strengthened, the energy balance began to tilt. Ice sheets, which took tens of millennia to reach their maximum extent, would soon enter a phase of rapid retreat. The world that had long been dominated by frozen continents was approaching a threshold, and once crossed, it would trigger a chain of events that reshaped climate, sea levels, ecosystems, and the fate of megafauna. The glacial world, vast and resilient though it seemed, was entering a period of instability that would ultimately decide which species survived the transition and which vanished entirely. The next phase would unfold with breathtaking speed, geologically speaking, and its consequences would echo across every continent. The first hints of a global shift began quietly. Temperatures in the northern hemisphere crept upward, driven by gradual changes in Earth's orbit that strengthened summer sunlight. The ice sheets, which had dominated the continents for tens of thousands of years, started absorbing more heat than they could reflect. What began as subtle surface melting soon expanded into deep structural weakening. The frozen giants were entering their final phase. Their collapse would not be graceful. It would be one of the most dramatic environmental transformations the planet has experienced since the rise of humankind. As solar energy increased, the margins of the great ice sheet softened, creating meltwater channels that carved deep tunnels under the ice. These channels grew into vast networks of subglacial rivers, lubricating the base of the ice and accelerating its movement. Entire regions of the Laurentide and Fennoscandian sheets began sliding toward the ocean, at speeds far beyond anything previously recorded in the glacial cycle. Icebergs calved in staggering numbers, releasing fresh water into the seas and altering salinity patterns critical to global ocean circulation. The response of the oceans was immediate. Meltwater diluted the North Atlantic, weakening the circulation system that distributes heat across the planet. This disruption triggered abrupt climate swings. Some regions warmed at unprecedented rates, while others cooled temporarily due to the breakdown of heat transport. The atmosphere struggled to stabilize. Storm tracks shifted, rainfall patterns reorganized, and coastlines transformed as sea levels began their long climb toward modern positions. The planet was entering an era of massive readjustment. On land, ecosystems unraveled with astonishing speed. The mammoth steppe, which had flourished during the cold peak, began fragmenting as warmer conditions encouraged the return of forests. Tundra retreated poleward. Grasslands shrank. Regions that had supported immense herds for thousands of years transformed into mixed woodlands and dense shrublands within a few centuries, an ecological blink of an eye. Cold-adapted species found themselves squeezed into shrinking habitats, struggling to keep pace with the rapid reorganization of the landscape. The mammoths, once the undisputed engineers of the northern grasslands, were among the first to feel the consequences. Their grazing and trampling had maintained open ecosystems by suppressing woody vegetation. As temperatures climbed and forests spread into their territories, mammoths lost access to the grasses and forbs that sustained them. Their migration routes broke apart. Calving grounds disappeared. Populations that had once stretched across continents were reduced to isolated pockets, each more vulnerable than the last. Woolly rhinoceroses faced similar challenges. Their specialized feeding strategies relied on snow-covered plains where they could sweep aside powdery drifts with their horns. But as snowpack diminished and shrubs colonized former steppe regions, the rhinos lost their competitive advantage. Fossil records show that their populations declined well before humans arrived in many of the areas where they once thrived, suggesting that climate pressures alone destabilized their long-term survival. In the Americas, the situation was just as dramatic. Giant ground sloths, mastodons, and glyptodonts faced habitats that no longer supported their needs. Forests expanded into regions that had been dominated by open prairies. Seasonal rainfall patterns shifted, altering plant communities and reducing the availability of nutrient-rich vegetation. Many of these animals had slow reproductive rates, which left them poorly equipped to rebound from sudden environmental shocks. Even slight changes in the timing of plant growth or the productivity of their ecosystems created cascading stress that populations couldn't overcome. But climate alone wasn't responsible for the final outcome. As ecosystems shifted, humans were spreading into new regions at a speed accelerated by the freshly exposed landscapes and expanding resource opportunities. Hunter-gatherer groups adapted quickly to changing environments. In Europe and Asia, humans exploited shrinking populations of large herbivores, using refined projectile weapons and coordinated hunting strategies. In North America, recently arrived human groups encountered megafauna that had never faced such technologically advanced predators. The combination of rapid climatic instability and human pressure created conditions that many species could not survive. Archaeological evidence shows that human populations expanded during the warm-up period, supported by diversified diets and new foraging strategies. Innovations included improved clothing, long-distance trade of stone and bone materials, and the use of traps and spears designed to target even the largest mammals. While megafauna had survived countless glacial transitions in the past, they had never faced these transitions with humans occupying nearly every major habitat. The overlap between shrinking ecosystems and expanding human activity greatly reduced the buffer that once protected these species during times of environmental stress. The collapse of the ice sheets proceeded in pulses. Some pulses caused dramatic sea level jumps within just a few centuries. Others unfolded more gradually, but all contributed to rising coastlines that reshaped continents. Low-lying areas flooded, coastal plains retreated, River systems reorganized as meltwater altered drainage basins. Many of the freshwater lakes formed along the edges of melting glaciers grew massive, held in place by temporary ice dams. When these dams failed, they unleashed catastrophic floods that carved canyons, scoured landscapes, and occasionally disrupted climate by injecting enormous amounts of fresh water into the oceans. One of the most significant events during this transition was the Younger Dryas, a sudden return to near-glacial conditions after the world had already begun to warm. It was likely triggered by a massive pulse of meltwater that disrupted the Atlantic circulation system. Temperatures in parts of the northern hemisphere dropped sharply for more than 1,000 years, only to rebound just as abruptly when the circulation recovered. These dramatic shifts placed additional strain on species already struggling with fragmented habitats and unstable climates. For humans, the Younger Dryas reshaped settlement patterns, forcing groups to migrate and adapt rapidly. In some regions, this disruption contributed to the early formation of agriculture, as communities sought stable food sources during a period of climatic unpredictability. As the ice sheets collapsed, new ecosystems emerged in their wake. Forests advanced into regions once dominated by tundra. Wetlands formed in meltwater basins. Rivers carved new pathways across freshly exposed land. Animals adapted to forested environments expanded their ranges northward. Species previously confined to warmer zones gained access to vast territories. The world that formed during this transition was more diverse, temperate, and dynamic than the glacial landscapes it replaced. Yet for many of the great Ice Age animals, these new ecosystems were not opportunities. They were obstacles. The decline of megafauna accelerated as the habitats they depended on continued to disappear. Even where climate conditions remained suitable, small isolated populations became vulnerable to disease, genetic bottlenecks, and increased human hunting. By the time climate stabilized into the Holocene, many species had already vanished. Mammoths persisted only on remote islands. Woolly rhinoceroses disappeared entirely. Ground sloths, glyptodonts, and saber-tooth predators followed the same fate. The giants of the Pleistocene left behind fossils, footprints, and layers of ancient DNA, but their world had passed. Humans stepped into the ecological gaps left behind. With the disappearance of large herbivores and predators, ecosystems restructured around smaller mammals and expanding human activity. Forests grew thicker without mammoths to knock down trees or maintain open plains. Grasslands declined. Nutrient cycling slowed as the massive biomass of megafauna vanished. The landscapes of the Holocene became fundamentally different from those of the Ice Age. The melting of the ice sheets was not merely an environmental event. It was a turning point that reset the planet's biological and climatic systems. It signaled the end of the Pleistocene and the beginning of the ecological and cultural landscape humans recognize today. The transition was abrupt on geological timescales, reshaping species, coastlines, and climates in ways that would define the next 12,000 years. The planet had entered a new era, one shaped no longer by the rhythm of advancing ice sheets, but by the expanding influence of a species that had learned to adapt, innovate, and transform its surroundings. The world left behind by the melting giants would become the foundation for human civilization. When the last remnants of the great ice sheets collapsed and the Holocene began, the planet entered a chapter unlike anything in its previous history. The world no longer operated under the dominance of continental glaciers. Instead, it shifted into a climate regime marked by relative warmth, seasonal stability, and expanding biological diversity. But the transition into this new era carried the weight of everything that had disappeared. The megafauna that once shaped entire ecosystems, the networks of migration erased by rising seas, and the ancient climatic rhythms that had governed life for millions of years. The Earth that emerged was familiar to modern eyes, yet profoundly altered by the legacy of the Pleistocene. As temperatures stabilized, forests advanced rapidly across the northern hemisphere. Birch, pine, spruce, and later deciduous oak and beech spread into territories long held by tundra and steppe vegetation. The mammoth steppe, once stretching across thousands of kilometers, fragmented into small patches before vanishing entirely. Wetlands formed in regions previously compressed under glacial weight. Soil profiles developed on freshly exposed land, creating fertile grounds for new plant communities. The once dusty atmosphere cleared as vegetation anchored the soil, reducing wind erosion and transforming barren plains into mixed habitats. Ocean levels continued to rise steadily for several millennia. Coastlines retreated, flooding former river valleys and transforming them into estuaries rich in marine life. The Bering Land Bridge, once a vast corridor populated by mammoths, bison, and human groups, disappeared beneath the Pacific and Arctic waters, severing the physical connection between continents. Island chains formed where high ground remained above the waves, hosting unique ecosystems shaped by isolation. In Europe, the British Isles separated from mainland Europe, creating ecological boundaries that influenced the spread of species for thousands of years to come. The decline of megafauna had lasting consequences that continued long after their extinction. Large herbivores, which once served as ecosystem engineers, no longer maintained open grasslands or transported nutrients across vast territories. Without mammoths to clear young trees or compress snow, forests grew denser and winter snowpack altered. In some regions, fire regimes changed as flammable vegetation accumulated. The absence of long-distance grazers reduced the cycling of minerals between different ecosystems, subtly shifting soil fertility patterns. Predator-prey interactions also reorganized as top predators lost their primary food sources and smaller carnivores filled the void left behind. These changes did not occur in isolation. Humans, now spread across every major landmass except Antarctica, became the primary drivers shaping landscapes. Their impact intensified as populations grew and tools became more advanced. Communities adapted to the new Holocene environment by diversifying their diets, developing fishing strategies along rising coasts, and exploiting the expanding forests for fuel, shelter, and food. River systems rich in fish, wetlands full of migratory birds, and mixed woodlands filled with edible plants created opportunities that shaped cultural development for generations. One of the most significant transformations began around 12,000 years ago, as climatic stability encouraged new methods of food production. The Younger Dryas, with its abrupt cold reversal, had shown the vulnerability of human populations to sudden environmental disruption. As the climate warmed again and rainfall patterns stabilized, some groups began manipulating plant species intentionally. The earliest domestication efforts emerged in multiple regions independently, in the Near East, East Asia, the Americas, and parts of Africa. Humans cultivated grains, managed wild stands of edible plants, and gradually shifted from nomadic hunting-gathering toward more settled lifestyles. Agriculture did not replace hunting immediately. Instead, it formed a hybrid strategy for nearly 2,000 years in many places. But as domestic crops became more reliable and settlement sizes increased, farming shifted from experiment to foundation. This transformation reshaped the ecological balance. Landscapes once managed by megafauna were now shaped by human hands, through clearing forests, irrigating fields, building terraces, and controlling water flow. The animals that survived into the Holocene adjusted to this new reality. Elk, deer, bison, and smaller grazers adapted to changing vegetation patterns. Wolves, bears, and large cats sometimes came into conflict with growing human settlements. Birds expanded their ranges across forested territories, while rivers filled with new species as warming temperatures allowed expanded migration routes. Yet the continuity of the Holocene ecosystem depended increasingly on human choices, rather than the automatic rhythm of glacial cycles. As millennia passed, the memory of the Ice Age became encoded in geological layers, buried bones, and fragments of ancient DNA preserved in permafrost. Scientists reconstructing this vanished world discovered that the transition between ice and warmth held clues not only to past climates but to future possibilities. Ice cores from Greenland and Antarctica revealed atmospheric histories stretching back hundreds of thousands of years, showing how carbon levels, temperature, and global circulation shifted with each cycle. Sediment layers captured traces of pollen, charcoal, and microscopic organisms, revealing where forests advanced, where fires burned, and how ecosystems reorganized after glacial retreat. These records revealed something striking. The Holocene climate is unusually stable compared to the vast oscillations of the Pleistocene. For more than 10,000 years, temperature fluctuations have remained within a comparatively narrow band. This stability created ideal conditions for agriculture, population growth, and eventually the rise of complex societies. Yet it also raised questions among scientists. If the planetary orbit continues to follow long-term cycles, what delayed the onset of a new glaciation? The answer lies partly in the natural variability of orbital geometry. Current conditions simply do not align to trigger a new glacial advance. But another factor is human activity. Land use, deforestation, and greenhouse gas emissions began altering atmospheric chemistry thousands of years ago, long before the industrial era. Rice cultivation released methane. Early agriculture changed carbon storage in soils. By the time humans reached large population densities, their cumulative environmental influence had begun to diverge the Holocene from the typical interglacial path. The megafauna extinctions also contributed indirectly. Without large grazers maintaining open grasslands, forest expansion in the northern hemisphere increased carbon storage, subtly modifying feedback loops that once encouraged glaciation. The absence of species like mammoths and bison altered how snow accumulated and melted, reducing conditions that favored ice sheet regeneration. Though not the dominant factor, these ecological shifts played a role in shaping the climate balance of the early Holocene. Today, the legacy of the Ice Age still surrounds modern landscapes. Many lakes trace their origins to glacial scouring. Mountain valleys owe their U-shaped profiles to the movements of ancient glaciers. Fertile soils in Europe, North America, and Asia derive from wind-blown loess deposits laid down during glacial periods. Island chains, river deltas, and continental shelves reflect the dramatic rise in sea level following the melting of ice sheets. Even patterns of human migration, language distribution, and cultural development carry echoes of the pathways opened or closed by ancient climates. Modern science continues to uncover clues from the Pleistocene, using advanced genetic techniques to reconstruct extinct species and track population movements across continents. Ancient DNA extracted from frozen sediments or preserved bones reveals how mammoth herds expanded and contracted, how human groups interacted with Neanderthals and Denisovans, and how ecosystems responded to rapid climate change. These discoveries reshape our understanding of evolution, showing that extinction is rarely caused by a single factor, but by the convergence of environmental pressure, habitat loss, and competition. The end of the Ice Age is often portrayed as a natural conclusion, but in reality, it marked the beginning of a new planetary experiment, one where humans became the primary force shaping ecological and climatic systems. While the great cycles of Earth's orbit continue, their influence is now intertwined with the actions of a species capable of altering its own environment on unprecedented scales. The stability of the Holocene provided the foundation for civilization, but understanding its origins requires looking back to a world ruled by ice, shaped by megafauna, and transformed by forces both celestial and biological. The echoes of that vanished world remain etched into coastlines, encoded in DNA, preserved in sediments, and written into the migrations that carried humanity across continents. The giants of the Pleistocene may be gone, and the ice sheets may have retreated, but their influence persists with every shift of the climate, every fossil unearthed, and every scientific discovery that connects the present to the deep past. The Ice Age did not simply end. It set the stage for all that followed, leaving a planet forever shaped by cycles of cold, warmth, extinction, and adaptation. Don't forget to subscribe. It really supports the channel and helps us bring you more great stories.